To know, you're all faculty and students. Have you studied linear algebra or matrix theory or equivalent courses in your during your engineering, or many of the teachers or faculty you might have been teaching that course? So I want to know what is your background. So what was that course?
So it was matrices, transforms.
Okay. These people, these are all students. Have you undergone any course on?
We had subject.
What is that?
Mathematics in that algebra, mathematics.
Okay. If I ask you, per se, I just throw a word, basis, you understand? Okay. Fine. So I think here and there you have some basic knowledge about linear algebra, etc. things. But I would like, before I start something, I would like to say certain things. What we call linear algebra in math perspective. In engineering perspective, it is like linear system analysis equivalent is that. So linear system analysis is a very fundamental for engineering, but linear algebra may be for science and other backgrounds. So it becomes so fundamental that we must undergo that course. If you are a faculty, some point of time you have to teach that course. If you are a student, graduate student, rather undergrad, so that you have to undergo that course, because that's very fundamental. That becomes a fundamental for nonlinear theory. So, and I used to say my students, linear algebra or linear system analysis, there is only one linear system theory. What I mean to say is there are varieties of nonlinearities. Okay, so the linear system theory, if you apply to hydraulics per se, or electrical engineering, or mechanical, or anywhere, the same theory is there. That is tuned to the background of whether domain of mechanical, electrical, etc. thing. So in that sense, the theory is well developed, and linear algebra, linear system theory is very nice and very beautiful, rather, in the sense, if you start reading linear algebra, it is so nice that you continue reading that because it is highly structured. We say wherever structure is there is beauty is there. Beauty in the structure, like. Okay, so it is not hard or difficult to undergo or understand the concepts of linear algebra and linear system theory. Certain remarks I have to say. In our engineering, we study signals and systems, probably electrical engineers, in the third semester or so. So in the third semester, that becomes more of a functional analysis rather. So without studying the fundamental matrix theory and linear algebra, we directly jump into the functional analysis type of a course. So that may not be correct, and we have to undergo in the discrete space, etc., matrix theory and other things before we jump into the continuous functions and function spaces, like. So that's the one thing. And as Professor said, I learned a lot of mathematics when I was in Indian Institute of Science. I have to be grateful to that. I would like to thank and acknowledge Indian Institute of Science for that, because it provided, rather, we learned a kind of research culture and academic culture there. So that's why it is a very great institute, because nowhere in India you find such kind of a culture. Okay, so that's another point I would like to mention here. Okay, so there's how to start this one is a problem, like. It's a way to start, like, because certain background, but for me, okay, I'll start somewhere like from the high school level. You have studied something like algebraic structures. I don't do too much of maths in this, but I would like to say very intuitively what it is like. Okay, everything starts with set. Okay, we understand what set is. Usually it's a non-empty set. Non-empty set, it gets a structure. Mathematically, structure means what? It satisfies certain properties. Okay, certain properties. A set satisfies certain properties, it gets the structure. So the algebraic structure is like that only. Yes, a set, non-empty set with certain properties. if the certain properties are depending on the structure, you call that as a group, vector space, rings, fields, etc., etc. It becomes more of an abstract algebra after that. So we have studied in the high school group structure. The sense given a set, okay, you all understand the set of numbers at least. Okay, set of numbers. What are the numbers? You have to interact with me. Tell me the number sets.
Real numbers.
From the very primitive. Natural numbers. Natural numbers, somebody will include 0, somebody will exclude 0. There are other things like that. After that, integers is there. Integers, rationals, irrational is there, reals and complex. At least until complex we can study that. So all these are infinite sets, right? So we do set operations so that we say this property is satisfied. Usually in the group structure what we take is a binary operation. Okay? Binary operation could be anything, right? So binary operation, we take two elements from the set and then do the binary operation. Per se, G is a set, non-empty set. G is not equal to 0. I write in this fashion. Suppose A comma B from the G, you do binary operation something like this. And the result, per se it is C. C should be belong to the G. Then it is called closure property, etc. Things you know. So like that, so we have binary operation, and you can do various, we can check various properties here, probably like closure property, associative property, all these you know. I don't want to go very elementary level there. Closure property, associative property. One more is existence of identity element. What is identity element? Per se A is there. To the E, it becomes EA to the, this becomes A. This is your identity property. And you know that for a set, identity element is unique, like. That's the one thing. And another important is the inverse of each element there. Inverse is unique for particular element. So each element has inverse. So we call, with respect to that binary operation, that is the inverse, okay? I write something like A inverse here, okay? A inverse is E. This is a property, okay? So a non-empty set with these properties called, it becomes a group, okay? It's a group. We can immediately, once we define group like this, we can give examples of groups, etc. The best example is a real, because real is a highly evolved number system. So by default, it becomes the answers to many of the questions. Okay, what I would say is you have to identify a very primitive set where it is just a group. Okay, like that. Okay, you can think. Fine. Once group is there, so okay. Before this, you can have monoid, etc. structures. Let us not go into that. At least we understand what group is. So next is, everybody, you have heard of vector space, right? Vector space. Mathematically, you can denote this as G with an operation here as a group. Like. Okay. So in the vector space, we need two binary operations. Usually we call vector addition and scalar multiplication. Okay. So vector space, again it is a non-empty set V with two operations, this and this. Now, with respect to addition, you can check these properties. With respect to multiplication, you have to be a bit careful here. Okay? And there is an interplay between addition and multiplication. Okay? So, vector space is a group with respect to addition. I define group here. I take this definition. Vector space is a group with respect to addition. So it has additive, identity, and inverse of each element is there. That's why we talk about zero element in the vector space and negative of an element in the vector space. That is with respect to group. The next one is this one, scalar multiplication. Usually the scalar, if I say this, scalar is from the field, okay? They call field. Usually it is vector space over a field. Field is another evolved algebraic structure. We'll see what field is. Okay, fine. So there are properties, 4 or 5 properties with respect to addition, 2, 3 properties here, and there is a distributive property which includes both plus and dot. Okay, so it could be left distributive, etc. Associativity with respect to scalar multiplication, those properties are there. So any standard reference you will get that. So what I would say is vector space is defined over a field or on the field where scalars are from the field and the elements x belong to V. This is a vector from this. Okay. So vector space has a group structure hidden, okay, inside this. Okay. Then there are other structures which is bit evolved than these rings, etc. Let us not go into that. But I just say here field because we use this, because vector space over a field, like we say. Okay, again I go back to the group. Okay, so field could be F is a letter for me. I use that letter. F is any set, non-empty set. Again it has 2 operations, this and this, addition and scalar multiplication. F plus dot. I have to be a little bit careful here. I can change this notation to V plus F dot usually. There is not too much bother about mathematicians' notations, but the notation is very important because notation takes you further. That's how it is. Matrix is a very nice notation rather. Okay, so vectors, this is the plus addition is with respect to this, dot is with respect to F. So this is a field. The first one is F plus is abelian. Abelian means commutative group. Commutativity you know. A binary B is B binary A is commutative property. So F plus is abelian group. Second one is F dot is also abelian group. Here when dot is nothing but it is multiplication, since it is a field, here it is a scalar multiplication. Okay, A into B, like that. So one thing here is this has additive identity and in additive inverse with respect of each element. Here you have multiplicative identity and as well as multiplicative inverse is there. Suppose I take a number 7 on the reals. What is the additive inverse of 7? Minus 7, because 7 plus minus 7 equal to 0, where 0 is the additive identity. Right? So what is the multiplicative inverse of 7? It is 1 by 7 because this is 1. This 1 is the multiplicative identity in this one. Okay? So, but when I have to be a little bit mathematically careful when I say this one. All non-zero elements have multiplicative inverse. That's the one. Otherwise you'll ask a question, what about 0? Like 1 by 0 is, it is undefined. Like. Fine. So this is a field. So field is more evolved than vector space. Okay. So but anyway, we deal with vector space, which is very nice structure. So vector space means it has 2 operations plus and dot. Okay. So this is a kind of a definition for. This is with respect to general mathematical object. We will see some examples for vector spaces. Okay. So the first thing is vector space is a non-empty set with binary operations. Okay, that's all. So now I'll ask you give certain examples of vector spaces. Give me some number sets which are vector spaces. For granted you can take field as real field. Right? Okay, probably one more thing I'll just say here. The arithmetic operations, these are there. Addition, subtraction, multiplication and division is there. You can ask the question whether can you do all these 4 operations on these structures. Okay. So here you are defining addition. Okay, binary operation is, if you define this binary operation as addition, probably additive inverse is there, so you can do subtraction. There's no multiplication, otherwise you have to say G plus G this. Okay? You have to consider group structure with respect to this, group structure with respect to this. That may not be, unless otherwise it is. So vector space, you have what? You can do addition, subtraction. Can you do multiplication? Is multiplication of two vectors defined in the sum? Maybe you can have element-wise definition and all, but suppose if I have a vector per se, before taking example, I'm saying the example here itself, you know the tuples, right? RK. RK means, RK is, what is RK? Everybody understand RK? Okay, you don't understand RK. Fine. What I mean to say, I'll come to that. So what I mean to say that you can do scalar multiplication, not the vector multiplication here. Only scalar multiplication. That means you take a vector x which is in V, you can take alpha which is in field, you can do alpha x, that's all. This alpha x belongs to, again, the V, closure property. But you cannot do to vector multiplication here. So when you come to field structure, you can do all four operations. Okay, you can do addition, subtraction, as well as, because there's a multiplicative group is here. Okay, this is a abelian group with respect to multiplication. That's why you are doing all this in the reals. We're on the reals. So 7 minus 7, 0, and 7 plus 0 is 7. And 7 into 1 is 7. 7 into 1 by 7 is 1. Okay, like that. So it is there. Fine. So let us go back to the vector space. Any question here? So that the summary is, all these algebraic structures are defined on non-empty sets and with certain properties. The properties are like, with respect to a binary operation, right? It could be usual closure property, associative property, existence of identity element, inverse of each element, commutative property if it satisfies, like this. Okay. So that's how you check the structure within the set. You just check the properties. If it satisfies, okay, that set gets that algebraic structure, like that. Okay, this is more algebraic way of saying this. There's a geometry there, right? Okay. So in geometry, we have more subjective feel for geometry than algebra. Algebra has more expressions, polynomials, etc., things. But our feeling for Euclidean geometry, plane, lines, are probably we have more subjective feeling for that. So we'll interpret that in terms of these things. Okay, so I'll just erase this. Okay, so let us go one by one per se set of real numbers. Let us understand Euclidean space first. Real line is this, right? There is some 0 here. This goes to plus infinity, this goes to minus infinity. You can have numbers on that. Okay? This is called a scalar. If you want representation, per se 1. Per se 1 is a vector notation here I'm using. Next is R2. What is R2? R2 is plane. You can call this x-axis or a y-axis, certain things like that. x1, x2 or whatever it is. This is the origin. Okay. Tuple notations. 1, 1, 2 belong to R. 3-dimensional is, what that is. If I write 1, 2, 3, okay. So these are very standard because, as I said, real number is highly evolved. You can have most of the structures. Here I say this is R1 because That 1 stands for something like dimension. We'll come to that. Okay, fine. So this is how the geometry is: real line, plane, and this. If you take any point on the real number, it is a vector per se. It could be 1. If you take any point here, you have corresponding and x and y, maybe 1 comma 1, like that. So every point. In your classification, you say, every it is a d-dimensional feature, it's a d-dimensional space on which you put that point, it becomes a scatter plot. Like that. Okay, like this in R3. So that you can do vector addition, scalar multiplication. Not like this. You cannot have 1, 2, 3 into 1, 2, 3 like. Unless you have your own definition and consequences of that. Otherwise, it is meaningless like. Okay, so this is not that. Okay, fine. In the vector space, there are like your feature vector and all these types of structures are very common. Like you have 100-dimensional features. They lie in 100-dimensional, probably Euclidean space. Okay, once let us go. Okay, so there are certain concepts notions in the vector space. We have what is known as linear combination, linear independence, linear dependence, linear span. A fourth one is basis. Fifth one is dimension. Okay, so you have heard of these keywords at least, right? What is linear combination? Okay. Per se, you have vectors x1, x2, x3 in some vector space V. Alpha 1, alpha 2, alpha 3 belong to the field because this is a vector space over the field. You have alpha 1 x1 plus alpha 2 x2 plus alpha 3 x3. This is linear combination. Okay. Alpha can take any real value. There's no restriction like otherwise it's convex sets and all, there are restrictions. So here it is no restriction. So this is linear combination. You know that linear combination is closed because it becomes another vector in the vector space, right? Okay, how many vectors are there in a vector space? How many? So many it is. Infinitely many, like, right? Infinitely many vectors are there. Per se, for an illustration purpose, I write something like this. This has some Rn. I'm not putting the boundary there, just for illustration purpose. And there could be a vector here. It's one point there. There are infinitely many vectors there. Infinitely many. Including zero vector. That's more important. Okay, the one requirement for a vector space is zero is there. Zero is everywhere, like. Okay. For example, if you substitute alpha here as 0, each alpha can take 0. It becomes a zero vector. Zero vector is there in the vector space. So that is a must. For example, in your linear system theory, you say, how do you check for linearity? Okay, I have to go to the transforms here, operators. Okay. So there is zero input, like zero input. Okay, finally it gives a zero output. That's a separate, I have to talk about linearity there. Fine. Once you have set of vectors, now you have set of vectors. S could be, I can say x1, x2, x3. Now you can talk about linear dependence, independence, all those things. If there is only one vector, what is that? It is linearly independent. There is no other guy to compare it with. Suppose there is a zero vector, only one zero vector. We say by default, by convention, we say that it is linearly dependent. Okay, but it's only one vector per se if you take. What is the use by taking that and all? We don't know. Mathematically simply asking the question. Okay. So a set may be linearly dependent, independent. You know the definition for linearly independent. What is that? You have suppose x1, alpha 1 x1 plus alpha 2 x2. Per se I just take two vectors. I want to get a 0 vector, that means alpha j is 1 and 2, has to be 0. Then you say x1 and x2 are linearly independent, right? Suppose at least one alpha is non-zero, what happens? You get linearly dependent set. Okay, what do you understand by linear dependent set? Per se, I give you three vectors. What is your understanding that linearly dependent? The set is linearly dependent. What do you mean by that?
What is given by linear combination?
For example, I'll give you a simplest example. You understand all this. Per se, these two are vectors. One more vector I'll give you this. This is a set of three vectors, x1, x2, x3. Okay, this is linearly independent set or a dependent set? I have to be a little bit mathematically careful writing. This is this, okay. Is this set linearly dependent or independent? Okay, I'll not go to that. I'll go here itself. 1, 2, 2, 4. Tell me. Oh. This is linearly dependent set because the second vector is twice the. Okay. Or you can say this plus this. Okay. Here, okay, twice actually the scalar. Here what happens? This vector is linear combination of this and this. So this is linearly dependent set. Okay. So, but there are other definitions I have seen. Usually I too got a confusion that in linear dependent set, my understanding was this, but I get corrected this. Any vector can be written as linear combination of other vectors. Like, is that definition, is that true? Linear dependent set is there. Our feeling is any vector in that can be written as linear combination of other, per se, two vector or whatever in this particular case, other vectors. So I got it corrected. The correct is at least one. It may not be for all. That means if you take x1, x2, x3, three vectors, it is not that x1 is written as linear combination of this, x2 is written as linear combination of this, x3 is written as linear combination of that. No. At least one can be written as linear combination. I'll give you a particular example. I don't have that this time. Per se, tomorrow I'll give you right on the board. Like. So at least one vector is linear combination of others. Okay. One is enough. May not be all like, it may not hold for all. Fine. Linear dependence, linear independence is over. Linear span. Span means what? Span means set of all linear combinations. I'll go back to geometry again. I'll just be in the plane R2. Per se, you know, in linear algebra, every vector starts from the origin. Beginning point is the origin, because that is how it is standardized or whatever. Okay, this is a vector. This vector is in 2 dimension. You have two components per se. This is 2 and 1. How do you get the span of this? I want to get the other vector by the only one important operation is linear combination. The linear combination includes scalar multiplication and addition is that, right? Okay. In that sense, in the vector space we have two important operations. One is addition and scalar multiplication. Okay. So what is linear span here? Suppose if I multiply this by alpha is positive, maybe greater than 1, you go toward that side. Whatever the alpha you choose, right? And negative alpha you can. So the span is this, the entire line. Okay, that is set of all linear combinations. This is per se, this is x equal to this, alpha x. Alpha can be anything from the field. Per se it is real now. Per se it is. This is a span. Suppose if I give two vectors, This is one vector, the other could be this vector. Now how do you construct linear span? Just like this only. So it is again linear combination. Okay. So suppose if I multiply this by 2, I'll be somewhere here. If I multiply this by 2 somewhere here, any scalar multiplication it will go here. And also addition is there. I can add these two vectors. You know how to add these two vectors, like tip to tail rule or whatever it is. Okay. This is a sum. I can add these two vectors like that. I can have this, and what happens? What is the span here? Okay. I can go here also. I can go here also. Okay. There are a lot of combinations possible. Okay. What is a span? Span, suppose it's the x1 vector, x2 vector. What is the linear span of x1, x2? Okay. So if x1 and x2 are linearly independent, it becomes the entire plane. Right? Entire plane. So that's why the basis definition is there. You can span the entire plane using just two independent vectors here. Okay, that is called linear span. Then, okay, we have defined linear independence and linear span. The definition for basis is told in terms of linear independence and linear span. So we know that every vector space has at least one basis is there. It might have many bases, infinitely many. So what is a basis then? What is basis? Basis gives you a kind of representation for any vector in the vector space, right? It has to be represented. Any vector, given vector has to be represented using basis vectors. Okay. So even though in a vector space there are infinitely many vectors, we don't want all infinitely many vectors. We want the basis vectors which are finitely many here. Okay. Even though the vector space has infinitely many vectors, okay, its dimension is anyway finite because it is the what? Cardinality of the basis set, we say. So what happens? This becomes a finite dimensional vector space. Okay. So what is basis then? The basis has to be linearly independent, first thing. The second one is it has to span the space. Okay. So in R2, first let's go to R1 only. This is R1, that's 0. You know the structure in this R1, there's only one component. R2, there are two components. You have to recognize these. 1, 2, 3 components are there. In n tuple means it is in n dimensional space, right? This is just a real line R. Anyway, if I have a 0 vector, I can't do anything with the 0 vector because 0 multiplied by anything is 0, right, like this. So I have to take a non-zero vector. Take a non-zero vector. Per se, 1 point, I don't take 1 because it's confusing every time. If you 1.2 will take. So 1.2, will it span the entire line is a question. Is it linearly independent? If these two properties are satisfied, it becomes a basis for R. Right? Given 1.2, which is non-zero vector, a single vector, it is independent. Okay. The next is, I have to get the span of this. Span of this is nothing but alpha times 1.2. Right? 1.2. Alpha can be anything. Positive, negative, 0 also it can be. So substituting value of alpha, you can span the entire real line. So one of the bases for R is 1.2. Now 1.2 is a basis. You can give many examples for basis for R or R1. Can anybody tell quickly? You can give your own basis. What is the basis for R? If I say 1.2, that is all. Okay, 1.2, only 1.2 is the basis for R? No. You can give any non-zero vector. Let's go to R2. R may be very simple example. Let's go to R2. Okay, in the R2, if I just give any one vector, will it span the entire R2? It will not, because you can move along the line, that's all. Okay, if I give you another vector in the same direction, even this fails. Okay, I have to give another vector such that this vector and this vector are linearly independent so that it spans the entire R2. So those two vectors become the basis for R2. Per se, if I can talk in terms of angle formed by this vector, suppose they are having some non-zero angle and not 180 degree. 180 degree. You understand what I'm saying? If I give you one vector somewhere here, another vector with an angle theta which is non-zero, but not 180. 180 means this becomes this. That spans the entire R2. The best example is your, standard vectors like this and this. This is 1, 0, right? 1, 0. This is 0, 1. This spans the entire R2. Okay. So like that, you can find basis for other Rn, Rk, whatever it is. And you know that if this is a basis, suppose this set B capital I, right? 1.2 is my set. Cardinality of B, the dimension of the space. Dimension of the space. Here I need two vectors, the dimension is 2. So in general, I need n linearly independent vectors. So that becomes the basis. So the dimension of the vector space is n. Okay. But I'll test you this. We are in R. I'll give you 1.2 and 2. Set is yes. Okay. What do you say about this? Is this a basis for R? Is a set linearly independent? You check first. (1.2) and 2. Can I get 2 from 1.2? Possible. I can find some alpha which gives me this. Or 1.2 from 2, it is possible. So these two are, this set is linearly dependent set, first of all. So it doesn't qualify to become the basis. Okay. But now, this is linearly dependent. If it is, okay, we have something excess here, right? You can remove the redundancy. It's a scanning process, either from left to right or right to left. It's your wish. So if I start from left to right, okay, I first choose the whatever available vector. I check whether this is linearly independent with this. Since this is not, I will discard this. You can do this for, if the set is having many entries, you can do this. In this case, I'll discard this. Finally, I'll get a linearly independent set. It becomes a basis. That means from the dependent set, if it spans the entire space, you can get the basis. The second property is a spanning. We know that 1.2 spans the entire R. What about 1.2, comma 2? Will it span the space? Why? Huh? Span means what? Linear combination. Alpha times 1.2 plus alpha 1 time, alpha 2 times 2. I can substitute alpha 1, alpha 2 from whatever any number. And you will get some number, no? This number, some number that will be somewhere on the line. It is possible to span the entire line using this also. This also. But there is redundancy is there. Okay. So you can have, okay, as I said, for basis this is enough. This is linearly independent and spans. But if you take linearly dependent or independent and a span, this is linearly dependent, but it spans the entire R. Okay, that subtle thing is there. So but there is a redundancy, you have to remove that if you want to extract the basis. So now I'll change the definition for basis. More optimal definition I have to have now. The basis is what? Maximal linear independent set, minimal spanning set. Okay, how do we say this? Look at this here. I can have 1, 2 also somewhere here, probably this is. If you look at this example, we are in R2. We know that we need 2 linearly independent vectors to span from our whatever the discussions. But what I say is, this is linearly dependent set. We know that. But it spans R2. Spans R2. How do you say about basis? Basis means there should be minimal linear independent set. Per se, the scanning process and choosing process we are saying. Per se, if I choose this one, and I'll check this with this. So this is linearly independent. So I have to include this, right? When I come here, this is linearly dependent with these two. Okay, I have to discard. Here also I have to discard. So these two minimal linear independent set and maximal linear independent set, maximal linear independent set and minimal spanning. Okay, minimal spanning otherwise, this also spans the entire R. So if I just give this one vector, it will not span the R2. So I need one more. So it is maximal linear independent from this direction, minimal spanning. Okay, so there are redundant representations in signal processing, like when you represent a signal, there are redundant representations are there. So the basis representation also, the basis is more optimal, just enough, just enough. Okay, we know the basis and dimension. So dimension is nothing but cardinality of the basis set. From this we know that there's R1, R2, Rn, Rk, whatever it is. Fine. So this is basis. Why basis? Using basis you can represent any vector in the vector space. That's one thing. But when I say this is some per se R2, if I recognize a point here, I have some coordinate for this, right? In that sense, suppose this is what? Minus, what is x? X could be minus 2, y could be minus 1, right? Minus 1? Oh, minus 1. To say minus 2 comma 1, that vector is already represented in some basis. In this case, it is standard ordered basis rather. Our standard ordered basis is what? X and y, your Cartesian coordinates. X and y, this is standard order. Standard because we suppose 3, 4 is a vector. You know, this is represented as 3. Okay, this is a scalar, this is a 2 axis. This is a standard basis. 3, 4, we recognize our convention. It's already represented using this basis. So whatever you write in the tuple form, it is assumed that there is standard order basis already. You can change the basis. You can have some other basis instead of standard basis. Suppose these two are the basis. Right? In the standard basis, what happens? If you're given a point, you project here and here, you will get a xy coordinates. Correct? Suppose there is this same point, I want to get coordinates for this basis. These two are my bases, right? So I have to correspondingly project, this is orthogonal projection, right? Project onto this and project onto this so that I'll get the coordinates. Okay. So you can change the basis and represent. But conventionally we are practicing this standard order basis. We have more subjective feeling for that. Okay, this is about vector spaces and their things. I have some, any question here?
You used R and F. How do you distinguish between them? Is it a set and a space or
Okay.
the same?
R as a vector space and F as a field, you may use. F is for field here. Field, when I say field is a scalar. Suppose I have R3 per se, R3. I take 1, 2, 3 as the entries of one vector. Each entry is from the field only. Okay, field only. And if I do alpha times this, alpha is from the field in this case. Alpha is from the field. But there could be differences. For example, I can talk about R. The vector space is R. The field may be, okay, I have to be a little bit careful. I'll put vector space as complex. A field could be real. Is it possible? To be a little bit careful here. Field is, scalars are from the real, vectors are complex. Okay. Or the other way also you can think and appropriately you can answer that one. Maybe set of all rationals. Rationals if I take, right? Rationals are vector space. Rational means what? A by B. A by B is a set of all rationals. I can have a negative of that is possible. A by B, identity, everything. Rationals are vector spaces. Correct? Set of all rationals. Now, rationals over the field. Okay, is rational a field? Okay, first I have to ask that question. Is rational a field? Yes, it is, because there is multiplicative identity, multiplicative inverse, everything is there. Rational is a field. Before you go to real, rational you get. Rational is a field now. So, now the vectors are from reals per se. Scalar is from rational. Or vectors are from rational, scalars are from reals. You can check these combinations. Usually, by default what happens is, we take from the same field, default is real, the entries are the real entries here. Otherwise I have to talk about rational or a specific integer kind of a cases. But that might not. So, by default we take both as reals in this case. But such questions can be asked, it's nice also.
So the alpha 1, 2, 3 could be said to be either from F or R1.
By default, R1. That's nice. Nice observation. So something could be a vector space over, usually suppose n tuples or vector space over reals we say. N tuples may be vector space over some other. Okay, I have to be a little bit careful in making that statement. But there are examples of that. The field is different, the vector elements are from the different like. But both are fields like. If I take rationals, rational is also a field. Reals is also a field. Vector elements may be rational. Scalar may be real. Okay. Fine. What I was saying then. Any question? Any other question? One more thing I want to say here is this linear algebra or whatever this linear analysis you study, this is irrespective of signal processing or image processing or your medical domain or something else. This gives you more analytical ability to deal with your research and other things. It should be like in our, when we were very kids and childhood days, our parents used to teach 1, 2, 3, 4 weekdays. It is called by heart, by pata and all we used to call in Kannada. Okay? It is like that now because you should know linear theory. So it gives you more confidence and more structured language for representing other things and posing problems. Okay? Okay, it's like that. So it's very fundamental. So linear theory is well established. You should know linear theory, whatever the domain you are in. Okay, that's the one thing. The second thing is vector space structure. I'll just put these objects. Okay, what is this? This is scalar. Okay, I'll write something like this: 2 tuple. This is 3 tuple. R1, R2, R3. I can have RK in general, right? RK. RK is a vector space over R. Next, I can have, this is a vector, I can have a matrix. In general, set of all matrices over Mn. Matrix elements far from the reals. So, set of all M by N matrices is also a vector space. Right? You can add 2 matrices, the result is another matrix in the reals. You can have a scalar multiple of a matrix, so it is also closed. So set of all real matrices of M by N forms a vector space. So what is the basis for this and what is the dimension of this? Okay. We talk about structure and other things. Suppose 1, 2, 3, 4, in many of our signal processing operations we make this as a vector, right? 1, 2, 3, 4, like 1, 2, 3, 4. Okay, the same structure is preserved actually in the linear algebraic sense. This dimension is Mn. Here it is 2 by 2 into 2 is 4 dimension. How much? Okay, if you know this representation, right? Basis representation for this. Quickly, if I use standard basis, what happens? Wherever that element is there, you make this. So what is the cardinality? What is the basis here? This one, this one, this one, this one. Cardinality is that 1, 2, 3, 4. There are 4 elements. What is the dimension of this? 4. In general, it is Mn. So these are all one type of math objects, if I call. Mn matrices are another type of objects. Next, I can have what I can have? Polynomials. Over reals again. So if I write a0 plus a1x plus a2x square, it's infinite polynomial. Okay. I can make this finite plus this is something like an x to the n. So I stop this. It's a finite degree polynomial. Now, set of all infinite degree polynomials. That's also vector space. Set of all finite degree polynomials, degree up to per se d or n, degree n, up to n. Okay, d used for dimension, I'll use this n. If you take set of all polynomials up to degree n, it includes all the polynomials of degree less than n also. That is a vector space. If you consider just set of all polynomials of degree n, it is not a vector space. Not a vector space. Okay. Can you identify the 0 element here? A negative of an element? What is 0 element in the matrix case? What is 0 element here? Let me just ask. What is 0 element in R3? Origin in R3 is 0, 0, 0. What is origin in 0 in here? 0, 0. What is 0 here? 0 here. What is negative of an element? What is negative of 1, 2? Minus 1, minus 2. Negative of this? Minus 1, minus 2, minus 3. So we identify 0 element and negative of an element. That's a group property. I ask you the same question for matrices. You have 0 matrices, right? Negative of a matrix is possible. So 0 element and negative of an element. 0 polynomial. 0 is a polynomial. That means P of x is any polynomial plus 0 and negative of a polynomial, I can take minus of this, no? Minus of p of x. Each element is negative of a polynomial. So that what happens? P of x plus minus p of x becomes 0. That's what it is. So polynomials is a vector space. Okay. Polynomials is interesting because its dimension is finite if I just restrict until n. Okay, what is the dimension? Okay, I'll just take this example. 1 plus 2x plus 3x square per se. It's a polynomial. So of degree 2, up to 2 it is. It's a one element I am writing. So this is a set of all polynomials of degree up to 2 is a vector space. What is the dimension of this? For dimension I have to have the basis for this. Basis are monomials. What are monomials? X to the 0. What is that? 1 into x to the 0, 2 into x to the 1, plus 3 into x to the 2. Okay, you can extract this. 1, x, x square, etc. Whatever the degree you want. That becomes the basis for polynomials. I can have finite dimensional polynomial space. What is the dimension of this? Where this polynomial lies? Which dimension? Or what is this is there? It is degree 2. It is in 3-dimensional because this is also there. So that's why this is equivalent to, this is an element in R3. We talk about isomorphism and etc. things like that. So polynomials, a finite dimensional vector space. But if your polynomial has a continuous function, it's a function space it becomes. Okay. So we have seen polynomials. Next is sequences. Not sequence. What is that? Sequence. What is sequence? It's a discrete signal like. You can have 1, 2, whatever, converging, diverging, whatever this is there. It's the extension of a vector. Finite vector, infinite sequence. Set of all sequences is a vector space. You can add 2 sequences. You can have 0 sequence. You can have negative of a sequence. After sequence, you have continuous functions, set of all functions. Okay, f of x and g of f1 of x, f2 of x, take 2 entries from the functions. You know how to add 2 functions element-wise. Even though they are continuous functions, our thinking is when adding point-wise addition. You can add 2 functions. You can have 0 is a function and negative of a function. All is possible. So we can like that we have to see. This is in the case of finite vectors, matrices, okay, polynomials of infinite, okay, and then finite degree. Many polynomials we use interpolation. Even our regression problem is polynomial fitting only, right? Then sequences is one side it is infinite, right? Okay. So sequence is a vector space and set of functions. Still you can classify subspaces, etc. But generally I speak, set of all functions also form a vector space like. So that you can add 2 functions, negative of a function, etc. you can do. And finding basis may be a little bit tricky in finite dimension. Okay, whatever the vector spaces here, they are all finite dimensional vector spaces. Polynomials, you can have infinite degree polynomial, it may go to infinite degree. Even if you take finite degree, if you take it as a function, you might have to deal with that as an infinite dimensional polynomial because it becomes a function. Sequence, there's infinite entries are there, right? Anyway, these functions are infinite dimensional vector spaces. Okay, for linear algebra, many at times our restriction is in the finite dimensional vector space, in a Euclidean space we will be. Okay, so you have to deal with vectors in finite or sequence in infinite case, or you have to deal with matrices. You can images and other things can be thought as matrices, etc. And then your discrete signals, sequence in terms of sequences you can interpret, and continuous functions like this. If you say a set of all continuous functions periodic, Fourier basis is defined for that, right? sines and cosines, or complex exponentials in the general sense. Okay. So any question? So the thing is, you have to deal with all these things for your signal processing or image processing in the general, very elementary linear algebra, as well as function spaces will come. That's why I say our signals and systems becomes a function space. Function space. So that is introduced at the third semester itself. Without knowing the finite dimensional spaces.
They are studying function analysis and they are studying.
Okay, any question? Okay, if there are no questions, I'll stop here. We have a tea break now, half an hour. We'll come back at 11 o'clock. Professor Raj will continue in 11 o'clock. Thank you.
Multiplication of vector is not possible. But we have vector dot product which leads to scalar.
Okay, nice question. There are only that exception is there, but the dot product becomes a scalar. It is not a vector. Even though there is entry wise, you do like this. Okay. Finally, suppose x1 and x2. x1 is in R3. x2 is also in R3 because it is there. So x1 dot x2. This is a scalar. It is not a vector. In that sense, it is not closed. You don't get the element here, right? Something else you get. That's a scalar. That is something else. So this is not closed in that sense. I mean, the one interpretation for that. That is a scalar.
Dot product or outer product?
So even in the matrix case, element-wise product is there. Matrix multiplication is a different thing is there. Okay? I mean, they are defined and their consequences, as a use I am saying, something else. But it is not an entry, not an element of the set again. If I mean, in this, at least in the dot product case, even if you add element-wise matrices, you get another matrix. That's all. But you have to again see the properties of that one to make it a structure. Otherwise it is taken as a matrix-wise multiplication and for your some purposes like.
Sometimes we take complex numbers to represent vectors or phasors.
Oh.
Then there's a bit of a mix-up in notation that we can multiply and add complex numbers and still visualize them as vectors. So that multiplication is different. It still gives you a complex quantity, but that's not the vector that you are talking about.
You mean to say cross product and other things? Yeah, it's there. Structure-wise per se, complex is R2. As per
But there is a J.
J is there, but you denote as real part and imaginary part. Each complex, C is nothing but R2 like as far as linear algebraic structure is concerned. That's why if this is 10 by 10 matrix, it is a 100 vector it is. So it is called isomorphism. So in that sense, I just make one line comment. All RK, finite dimensional spaces, are equivalent, like they are isomorphic. They have the same structure, the same idea you can use for this thing. Isomorphic means what? Iso means same, morphic means structure, right? Same structure they have. Like that, as you said, polynomial case. Suppose if I have only this is an R3 element where you have A0, A1 and A2. R3.
So we have to distinguish between the dimension of the coefficients in that polynomial and the dimension of that variable x. The power.
Here x is just an indeterminate, it's called, because it's a placeholder or something like it. Just okay. This has one basis. It could be a constant. This is having some linear variation. This has some quadratic variation in terms of. Okay.